Hello, this is Yin Ge. I'm from the Department of Chemistry at Central Washington University. My topic today is dissecting the polymorphism of chemical potential numerically and analytically. So, first, what is potential? Potential is the ability to develop or succeed in a dictionary. More generalized definition of potential is the ability to evolve with time. Now, what's chemical potential? It's a chemical's ability to evolve with time. As a chemical evolves, its ability to further evolve decreases. And this statement is equivalent to the second law of thermodynamics. And here's a short proof. As this ink evolves, its ability to further evolve decreases. The same principle applies to human. As a kid grows up, its ability to further evolve decreases. So I'm pretty sure when I reach 125 years old, my ability to further evolve decreases. Again, what is a chemical potential? What's the change of chemical potential? What's the trend of chemical potential? During a physical change, species always turns from the phase with a higher chemical potential to that with a lower chemical potential. In a chemical reaction, we can say the same thing. The species with a higher chemical potential always turns to those with a lower chemical potential. The chemical potential is very unique. It's the best criterion of spontaneity. It's even better than internal energy, enthalpy, Helmholtz energy, or Gibbs energy. Although we typically say, under the constant temperature and pressure condition, the Gibbs energy of a system obviously decreases, or we can also say, like in a isolated system, the entropy always increases. It's another criterion of spontaneity. But chemical potential is unique. It's the central piece of UHANG. So here's a visual example of chemical potential of water changes from higher to lower. And over here, again, water evolves. Its chemical potential changes from higher to lower. Again, it's water. I don't know what's going on here, but again, water evolves from a higher potential region to a lower potential region. We can add a Bunsen burner on the bottom, or we can just assume there's a vacuum pump being operating and sucking water out. But anyway, in either case, water evolves from a higher potential to a lower potential. Another example, when hydrogen and oxygen react, they become water. So in essence, it's from higher chemical potential to lower chemical potential. When we have photons, water can absorb photon and evolve into hydrogen and oxygen. In this case, water plus photons have higher chemical potential. Hydrogen and oxygen have a lower chemical potential. What's the UPAC definition of chemical potential mu? Well, here's a simple example. If we have a binary mixture of only two species, and if the condition is constant temperature and pressure, mu is simply delta G over delta N. More generally, if we have 500 different chemicals, we can say dG is equal to negative S dt plus VdP plus the sum of mu I dNi. Mu I is the chemical species, I's chemical potential. And also we can say the chemical potential mu is delta G over delta N under constant temperature and pressure condition. We do have to hold the amount of all other substances constant. The chemical potential is a central concept in thermodynamics. So here's a diagram. We have internal energy, enthalpy, Helmholtz energy, and Gibbs energy. Mu sits at the center. And among U, H, and G, there are 8 equations that relate them to each other. For example, G is H minus Ts, G is also A plus PV. Now let's look at the equations for chemical potential. First, the U-pact definition. dG is equal to negative SdT plus VdP plus the sum of mu I dNi. Again, mu is the chemical potential. So if we have constant temperature and pressure condition, we see dG is simply the sum of mu I dNi. And then if we hold the amount of all other substances into constant, and then dG is just mu times dN. Now we can go from dG to dA only because G is simply A plus PV. So we get this equation, and then we know A is U minus Ts, and H is U plus PV. So not only we get this U-pact definition of chemical potential, we also get 3 other chemical potential definitions based on H, U, and A. Now let's look at this equation. If we can hold entropy and pressure constant, and then dH is the sum of mu dN. If we can hold temperature and volume constant, dA is the sum of mu dN. Now let's look at the chemical potential again. It's simply how U, H, G, or A changes with the amount of the substance. But which one? It depends on the conditions. If the entropy and volume are constant, mu is delta U over delta N. If temperature and volume are held constant, mu is delta A over delta N. Again, this is U-pact definition. Mu can be delta G over delta N under constant temperature and pressure condition. In the end, mu can be even delta H over delta N under constant entropy and pressure condition. Again, mu sits at the center of this wheel of U, H, and G. And we can have a unique and the best criterion for spontaneity for any physical change or chemical equation, which is this: the sum of mu dN should be less than 0. That's the direction of spontaneity. But again, if we took general chemistry or physical chemistry, we learned that Gibbs energy always decreases if the temperature and pressure are held constant. Some of us have learned in physical chemistry that at constant temperature and volume condition, do not use G, use A. The Helmholtz energy always decreases. Rarely we have learned this: at constant entropy and pressure condition, enthalpy decreases. Under constant entropy and volume condition, internal energy decreases. And regardless of the condition, actually the criterion for the spontaneity of any chemical reaction or physical change for a closed system can be written simply as this: the sum of mu dN is negative. Other than the previous 4 equations of chemical potential, there's another one. Chemical potential is how entropy changes with the amount of the substance. So let's look at this. We have learned that mu is delta N, delta U over delta N, and then we can simply use the triple product rule in multivariable calculus and do this derivation. And this part is simply temperature. Delta U over delta S is temperature under constant volume condition. So we have negative T here, and now we can see the chemical potential is expressed in terms of entropy. It's delta S over delta N times negative T. Now number 6 equation, mu is negative T times delta S over delta N under constant enthalpy and pressure condition. So if you look at these 2 equations, both equations have this chemical potential mu expressed in terms of delta S over delta N. However, the conditions are different. Over here, we have constant internal energy and volume. Over here, we have constant enthalpy and pressure. We're not done yet. There are 6 more equations for the chemical potential. The chemical potential is also how pressure, volume, or temperature changes with the amount of the chemical. So mu can be expressed as delta T over delta N in two different ways, delta P over delta N two different ways, delta V over delta N in two different ways. That's a lot. But let's accept the polymorphism of chemical potential. We do prefer the UPAC definition. Mu is delta G over delta N under constant temperature and pressure condition. Two reasons. One is that temperature and pressure are intensive properties. It's fairly easy to keep the temperature and pressure constant while we just change the amount of the chemical. Another reason is more practical. It's easier to have constant temperature and pressure condition when we do chemical or physical experiments. Again, I understand it's very hard to accept the polymorphism of the chemical potential. But how do we convince our students that the chemical potential can be expressed in different forms? Or how can we convince ourselves? Now I'm going to give a total of 3 examples, 2 numerical calculations, and 1 analytical derivation. In the numerical calculations, I'm going to use delta G over delta N to calculate mu. I'm going to use delta A over delta N to do the same thing, and in the end, we get the same, exactly same result. And in the end, I'm going to use an analytical derivation to show you mu is negative temperature times ds over dn. So chemical potential is just how entropy change with the amount of the substance. And this, again, is related to the second law of thermodynamics. The entropy goes up, the chemical potential goes down. Look at this negative sign here. So first, numerical calculation, mu is delta G over delta N. We'll just calculate the chemical potential of helium in a 1 bar mixture of 0.4 mole helium and 0.6 mole argon at room temperature by adding a very small amount of helium under constant TP condition. So we add this helium into the system, and then we have new pressures for helium and argon. They are both slightly changed. And then we can calculate this delta G numerically. It consists of 3 parts. First, the change of argon because the pressure of this argon changes. And then we can calculate the change of Gibbs energy of the old helium, this 0.4 mole helium, and then the Gibbs energy of the new helium. And then we sum it up. We get delta G divided by delta N, which is this one. We get a numerical result. And this is really close to the result from the analytical expression of the chemical potential of this helium. Now we can do mu equals delta A over delta N. Same condition, we have 1 bar mixture of 0.4 moles of helium and 0.6 moles of argon. And this time we also add a very small amount of helium, only 0.00001 mole helium. This time the condition is different. It's constant temperature and volume condition. So under this constant temperature and volume condition, mu is delta A over delta N. Again, we calculate the pressure change. We calculate the Helmholtz energy change of argon, of the old helium, of the new helium. We put them together. We do a division. We get this number. Again, it's very, very close to the almost exact result from the analytical expression of chemical potential. So both numerical calculations result in the same result. Now finally, some analytical derivation. I'm going to prove this to you. Mu is negative T times ds over dn. Again, we're going to just do some calculation. We'll add a small amount of helium into a mixture of helium and argon on a constant enthalpy and pressure condition. So after the addition, we can actually compute the entropy change of the entire system on a constant HP condition. We get this expression. I skipped actually many steps over here due to the time limit. I'll submit the detailed derivation as the supporting information or supplementary material. And then we calculate this mu, it's negative T times ds over d in helium. The final result is this. Is this correct? Is this expression correct? So again, we got this expression, and then realize this, if we use this equation, we assume the molar Gibbs energy in the standard condition is just the Gibbs energy of formation in the standard condition, and we can have this molar entropy to be zero. And then we can convert this equation to this equation with some decent derivation, easy derivation, but decent derivation, because this mu naught zero, this is standard chemical potential, is simply the molar Gibbs energy of helium under standard condition. And again, we assume these two are equivalent, so we get this equation. And we know the Gibbs energy of formation of helium in the standard state condition is just zero. So basically, I was just saying this part is zero, this part is zero. So we have this equation equivalent to this equation. All right, we do not have to assume the molar Gibbs energy is equal to the Gibbs energy of formation. This time, we can redefine molar Gibbs energy to be the enthalpy of formation minus temperature times the molar entropy of the species. All right, but we will again get this same expression for the chemical potential. It's just mu superscript 0 plus RT times the logarithm of the actual pressure of helium over P naught. Why is that? This time, this part, this negative T molar entropy, it's not zero because we learned that from the third law of thermodynamics. This part is zero only at 0 Kelvin. At any finite temperature, the molar entropy of helium is positive, so this part is negative. But again, we'll get the same expression for the chemical potential of helium, only because in this case, when we assume the molar Gibbs energy is the enthalpy of formation minus temperature times the molar entropy of the species, we'll get this equation. All right, the standard chemical potential of helium is equal to the molar Gibbs energy of helium. It's the enthalpy of formation of helium minus the temperature times the molar entropy of helium. And because this part is zero, we delete this, and we have mu naught is equal to negative T times this molar entropy in the standard condition. So we can replace this part with mu naught, and we get the same expression for the chemical potential. So no matter what we do, we get the same expression for the chemical potential. I showed you three different conditions: constant Tp, constant Tv, and constant Hp. You can do constant UV yourself in some other conditions, but in the end, you will get the same expression like this. So in the end, let's embrace the polymorphism of chemical potential, whether it's constant temperature pressure, constant temperature volume, or constant enthalpy pressure condition. Whether it's numerical calculation, analytical derivation, we'll get the same thing. And that's good, that's self-consistency. But still, let's consider using the UPAC definition of chemical potential in PChem teaching and learning for convenience, but let's also embrace its polymorphism. Because the chemical potential is unique, it's the central place in thermodynamics. It connects all those thermodynamic properties, UH, A, and G, and also PVT and S. I will also present another oral presentation titled Open Access Editable and Multimedia Aided Physical Chemistry Textbook. And in this book, the chemical potential is covered in section 5.9. Feel free to use my PChem textbook in your class or modify it as you see fit. You can get the book from this website. It's my first name -last name.com, and let me know what you think.